So in the previous videos we have learned about monosaccharide chemistry, and now in this video we will learn about disaccharide, trisaccharide and polysaccharide. Disaccharides. A disaccharide is a glycoside in which the anomeric hydroxyl group of one monosaccharide is bonded by an acetal linkage to any of the hydroxyl groups, which may be anomeric hydroxyl or may be any one of the alcoholic hydroxyl group of a second monosaccharide. There are three types of glycosidic bonding arrangements in disaccharides. The first one is the 1,1- linkage. The first one is the 1,1- linkage. The anomeric carbon of the first sugar molecule is bonded through an oxygen atom to the anomeric carbon of the second sugar molecule. The 1,1- linkage is present in sucrose. So this is the structure of your sucrose, and this is the anomeric carbon for the first molecule, and this is the anomeric carbon for the second molecule. See, this one is the 1 carbon, this one is the 2, this one 3, this one 4, this one 5, and this one is the 6. Similarly, this one is the 1 dash, this one is the 2 dash, 3 dash, 4 dash and 5 dash. So the bonding is between the 1 and 1 dash carbon. One 4- linkage. The anomeric carbon of the first sugar molecule is bonded to the oxygen atom on C4 of the second sugar molecule. The 1 4- linkage is present in cellulose, maltose and lactose. So this is the structure of cellulose, where you can see this one is the 1, 2, 3, 4, 5 and 6 carbon. Similarly, this one is the 1 dash, which is the hemiacetal carbon. This is the 2 dash, 3 dash, 4 dash, 5 dash and 6 dash. So the bonding is between this 1 carbon and this 4 dash carbon. That's why this is the 1 4- linkage. 1 6- linkage. The anomeric carbon of the first sugar molecule is bonded to the oxygen atom on C6 of the second sugar molecule. The 1 6- linkage is present in zentiobiose. So this is your zentiobiose or centiobiose, and this is the 1 6- linkage. This is the 1 6- linkage. Now see, this one is the first carbon, which is the acetal carbon here, and this one here is the hemiacetal carbon, and this 6- carbon is giving its OH for the bonding. Now here you can see the IUPAC name of sucrose, maltose and lactose. Now sucrose can be said alpha D glucopyranosyl beta D fructofuranose, or even you can say beta D fructofuranosyl alpha D glucopyranose. Maltose is called 4O alpha D glucopyranosyl alpha D glucopyranose, and lactose is called 4O beta D galactopyranosyl alpha D glucopyranose. And this is the list of some important disaccharides. You can just note it down: sucrose, trehalose, maltose, cellobiose, lactose, zentiobiose and mellibiose. In different books you will get different nomenclature system, but this is the best one. So don't be confused if you see any mistake in any other book. Just follow this nomenclature. Sucrose. Ordinary table sugar is a disaccharide called sucrose. Sucrose, the most widely occurring disaccharide, is found in all photosynthetic plants and is obtained commercially from sugarcane or sugar beets. This is the structure of sucrose, where you can see the glucose unit is bounded with the alpha bond, and this fructose unit is bounded with the beta bond. You know, in Howard's projection, the upward bonds are the beta bonds. The structure of sucrose is based on the following evidence. Sucrose has the molecular formula C12H22O11. Acid catalyzed hydrolysis of 1 mole of sucrose yields 1 mole of D-glucose and 1 mole of D-fructose. Sucrose is a non-reducing sugar. It gives negative tastes with Benedict's and Torrance solutions. Sucrose does not form an osacone and does not undergo mutarotation. These facts mean that neither the glucose nor the fructose portion of sucrose has a hemiacetal group. Thus, the two hexoses must have a glycosidic linkage that involves C1 of glucose and C2 of fructose. For only in this way will both carbonyl groups be present as full acetals. Now, invert sugar. This is a very important thing. Invert sugar. When sucrose is hydrolyzed by dilute aqueous acid, it yields equimolar mixture of D-glucose and D-fructose. Since D-fructose has a greater specific rotation and the D-fructose has the negative specific rotation, whereas the D-glucose has the positive specific rotation. So positive for glucose and negative for fructose. And fructose has greater specific rotation in case of its magnitude. The resulting mixture is levorotatory. So you are hydrolyzing sucrose and you will get a equimolar mixture of glucose and glucose and fructose. This hydrolysis accompanied by a change in the sign of optical rotation from positive to negative is called inversion of cane sugar. The solution is also called invert sugar. Because fructose is sweeter than sucrose, invert sugar is sweeter than sucrose. So the optical rotation of sucrose was plus, but whenever you are just hydrolyzing it with some aqueous acid, it gives glucose and fructose. As the optical rotation of the fructose is higher than glucose, that's why this whole mixture will have a negative optical rotation. So you have taken the positive optical rotation and you have got a mixture which has the negative optical rotation. That's why this is called invert sugar. Most common form of invert sugar is honey, a supersaturated mixture of glucose and fructose. D-glucose has a specific rotation of plus 52.7 degree and D-fructose has a specific rotation of minus 92.4 degree. The specific rotation of invert sugar is half of the sum of those two individual monosaccharides. So this is the value of the specific rotation of the invert sugar, minus 19.9 degree. This is the Fisher projection of sucrose, and this one is the chair conformation for glucose and Howard's projection for fructose, and this one is both the Howard's projection for glucose and fructose. So these are the representation of sucrose. Trehalose. Trehalose is a sugar consisting of two molecules of glucose as 1,1 linkage. It is also known as mycose or tremalose. Some bacteria, fungi, plants, and invertebrate animals synthesize it as a source of energy and to survive freezing and lack of water. Trehalose has high water retention capabilities and is used in food, cosmetics, and as a drug. So this is the structure of trehalose, where the linkage is 1,1 linkage and both are just glucose unit, glucose plus glucose with the 1,1 linkage. This is the trehalose. Maltose. The structure of maltose was deduced based on the following evidence. When 1 mole of maltose is subjected to acid catalyzed hydrolysis, it yields 2 mole of D-glucose. Unlike sucrose, maltose is a reducing sugar. It gives positive taste with Fehling's, Benedict's and Torrance solution. Maltose also reacts with phenylhydrazine to form a monophenyl osazone. That is, it incorporates 2 molecules of phenylhydrazine. Maltose exists in 2 anomeric forms. Alpha maltose, which has an optical rotation plus 168 degree, and beta maltose, which has an optical rotation plus 112 degree. The maltose anomers undergo mutarotation to yield an equilibrium mixture with the optical rotation plus 136 degree. Facts 2 and 3 demonstrate that one of the glucose residue of maltose is present in a hemiacetal form and the other therefore must be present as a glucoside. The configuration of this glucosidic linkage can be inferred as alpha because maltose is hydrolyzed by alpha glucosidase enzyme and not by the beta glucosidase enzymes. So this one is the alpha linkage. Just see it here. This one is alpha, this one is also alpha, but they are specifying just the glucosidic linkage. Now this OH, this one is the hemiacetal carbon, and this OH or this hemiacetal group is responsible for the mutarotation and osazone formation for the reducing property of this maltose. And this is the acetyl carbon which is forming the glycosidic linkage, 1,4 glycosidic linkage, and this is the structure of your maltose. This will be alpha, okay, this will be alpha. I have forgotten to change this. Maltose has a free hemiacetal ring. This hemiacetal is in equilibrium with its open chain form. Because of this, maltose is a reducing sugar and exhibits mutarotation. So this is the maltose structure, chair form, and this is open chain aldehyde form. You can see this one is the open chain form. Because of this aldehyde can reduce those solutions, Benedict solution, Torrance solution, and that's why maltose can show reducing property and also mutarotation. Osazone of maltose. So this is the maltose osazone. You can see that the acetyl carbon is the acetyl carbon is not reacting here. Actually the hemiacetal carbon, which was the hemiacetal carbon, that is reacting with the phenylhydrazine, and the acetyl carbon is intact here. This is your maltose. This is your maltose, and this, if you just add bromine water, this will be oxidized to maltonic acid, and then you can add dimethyl sulfate, and then you can just hydrolyze it. And if you go here, take maltose. What is happening? Something is wrong. Yes. Take maltose, then give methanol in acidic condition, then just add dimethyl sulfate, then you will get this one. If you hydrolyze it, you will get this tetramethyl D-glucose and trimethyl D-glucose. Lactose. Lactose is a disaccharide present in the milk of humans, cows, and almost all other mammals. Lactose is a reducing sugar that hydrolyzes to yield D-glucose and D-galactose. So this is the structure of your lactose. This is the lactose, and this one is actually the galactose unit. This one is the glucose unit. So galactose unit is bound with the beta linkage. This one is the beta linkage, and the glucose unit has the alpha linkage. So the name is 4O beta D galactopyranosyl alpha D glucopyranose. Bromine acid oxidation of lactose. If you take lactose, the hemiacetal group is in the glucose unit. Okay. So if you add bromine water, then this group will be oxidized to give lactobionic acid. And this acetal linkage will remain intact. This one is intact. Osagon of lactose. If you react phenylhydrazine with lactose, then this galactose part will remain unchanged because it contains the glycosidic linkage, and this glucose part will form the osagon because it bears the hemiacetal group. Cellobiose. This is the structure of cellobiose. You can see this one or this one. The first linkage is the beta glycosidic linkage, and this one is the alpha linkage. Now cellobiose unit in cellulose. Actually cellobiose can be obtained from the hydrolysis of cellulose. So this is the cellobiose unit in cellulose. Partial hydrolysis of cellulose gives the disaccharide cellobiose, which has the formula C12H22O11. Cellobiose resembles maltose in every aspect except the configuration of its glycosidic linkage. Cellobiose, like maltose, is a reducing sugar that on acid catalyzed hydrolysis yields 2 molar equivalents of D-glucose. Cellobiose also undergoes mutarotation and forms a monophenyl osagon. Methylation studies show that C1 of one glucose unit is connected in glycosidic linkage with C4 of the other, and that both rings are 6-membered. Unlike maltose, however, cellobiose is hydrolyzed by beta glycosidase enzymes and not by alpha glucosidase enzyme. So, cellobiose is hydrolyzed by beta glucosidase and not by alpha glucosidase. This indicates that the glycosidic linkage in cellobiose is beta. Xanthobiose. Xanthobiose is a disaccharide composed of 2 units of D-glucose joined with 1,6-beta linkage. It is a white crystalline solid that is insoluble in water or hot methanol. This was first obtained from trisaccharide xanthanose. So this is the structure of xanthobiose. You can see this one is the beta linkage and this is the number 1 carbon, and this is connected with the hydroxyl group of the 6 carbon. So 1,6- linkage. This is the 1,6- linkage. Melibiose. Melibiose is a reducing disaccharide formed by an alpha 1,6 linkage between galactose and glucose. So this is the structure of galactose and this is the glucose. It differs from lactose in the chirality of the carbon, where the galactose ring is closed and that the galactose is linked to a different point of the glucose moiety. This is obtained from the trisaccharide raffinose. So if you go through the partial hydrolysis of raffinose, you will get this melibiose, which contains 1 unit of galactose and 1 unit of glucose. Here the linkage is, this one is the 1 and this one is the 6 carbon. So 1,6 linkage, where this galactose ring contains the hemiacetal. Sorry, the galactose ring is the glycosidic linkage and this glucose unit contains the hemiacetal unit. Trisaccharide. Manninotriose. Manninotriose contains 2 units of galactose and 1 unit glucose. It is the only reducing trisaccharide that has been isolated from natural sources. This is the structure of manninotriose. All the others of this group have been obtained by degrading polysaccharides or by synthesis. For example, cellulotriose from cellulose, and this is the manninotriose is the only reducing trisaccharide that has been isolated from the natural sources. Two important non-reducing trisaccharides are raffinose and xanthanose. Xanthanose. Molecules are linked in the following order: glucose, glucose and fructose. So in case of xanthanose structure, this one is the glucose, this one is the glucose and this one is the fructose unit. Xanthanose is a trisaccharide composed of beta D-glucopyranose, alpha D-glucopyranose and D-fructofuranose units. So this one linkage is the beta linkage, this one is the, okay, just let me clear this. This one is the beta linkage, this one is the alpha linkage, which contains the glycoside with this fructose. This unit is the, this linkage is the alpha linkage. It has a role as a plant metabolite. So this is the xanthanose structure. This is the xanthanose structure, from which you can separate the xanthobiose part. So this too is the xanthobiose, and this is the trisaccharide xanthanose. Raffinose. This is the structure of raffinose. The molecules are linked in the following order. This one is the galactose unit, then the next one is the glucose, and this one is the fructose unit. So this is the structure of raffinose. Actually, this is the structure of raffinose in the Haworth projection, from which you can separate melibiose. These two forms the melibiose part. So from the trisaccharide raffinose, you can get the disaccharide melibiose. It can be found in sugar beet, cottonseed, beans, cabbage, broccoli, and in other vegetables and whole grains. Artificial sweeteners. Sucrose and fructose are the most common natural sweeteners. We all know, however, that they add to our calorie intake and promote tooth decay. For these reasons, many people find artificial sweeteners to be an attractive alternative to them. Aspartame. This is the structure of aspartame, which is a popular artificial sweetener. The most successful and widely used artificial sweetener is aspartame, the methyl ester of a dipeptide formed from phenylalanine and aspartic acid. So it contains a phenylalanine structure and the aspartic acid. Aspartame is roughly 100 times as sweet as sucrose. It undergoes slow hydrolysis in solution, for which soft drinks should not be used after a certain limiting time. Because in the soft drinks, aspartame is present, so soft drinks should not be used after a long time, because the aspartame is actually hydrolyzed. It also cannot be used for baking because it decomposes with heat. So if you apply heat, this will decompose, and you should not intake those decomposed materials. Alitame. This is the structure of alitame. It is more stable than aspartame and roughly 2000 times as sweet as sucrose. Sucralose. Sucralose is a trichloro derivative of sucrose that is an artificial sweetener. Like aspartame, it is also approved for use by the US Food and Drug Administration. So FDA has permitted to use the sucralose in the foods. That means if you intake sucralose, that will not make any harm in your body. This is the sucralose, where this is the trichloro derivative. This one is chlorine, this one chlorine, this one chlorine. Sucralose is 600 times sweeter than sucrose and has many properties desirable in an artificial sweetener. Sucralose looks and tastes like sugar, is stable at the temperatures used for cooking and baking, and it does not cause tooth decay or provide calories. So it doesn't cause tooth decay, doesn't provide very much calorie, and this is also stable while cooking and baking. So that's why sucralose is used in food ingredients. Sucronic acid. Sucronic acid is a synthetic compound. Sucronic acid is 2 lakh times as sweet as sucrose. So this is very large amount, right? And this is the structure of sucronic acid. Cyclamate and saccharin. At first look at the structure of cyclamate, and this is the saccharin. Cyclamate and saccharin, used as their sodium or calcium salts, were popular sweeteners at one time. A common formulation involved a 10:1 mixture of cyclamate and saccharin that proved sweeter than either compound individually. Tests showed, however, that this mixture produced tumors in animals, and FDA subsequently banned it. So cyclamate and saccharin, these actually were used one time, but now these are banned by FDA, Food and Drug Administration, which is in USA. Polysaccharides. Polysaccharides, also known as glycans, consist of monosaccharides joined together by glycosidic linkages. Polysaccharides that are polymers of a single monosaccharide are called homopolysaccharides. Those made up of more than one type of monosaccharide are called heteropolysaccharides. So one is the homopolysaccharide, another one is the heteropolysaccharide. Homopolysaccharides are also classified on the basis of their monosaccharide units. A homopolysaccharide consisting of glucose monomeric units is called a glucan. One consisting of galactose units is a galactan. Three important polysaccharides of glucans are starch, glycogen, and cellulose. Starch is the principal food reserve of plants, glycogen functions as a carbohydrate reserve for animals, and cellulose serves as structural material in plants. Now start with starch. Starch occurs as microscopic granules in the roots, tubers, and seeds of plants. Corn, potatoes, wheat, and rice are important commercial sources of starch. Heating starch with water causes the granules to swell and produce a colloidal suspension from which two major components can be isolated. One fraction is called amylose and the other amylopectin. Most starches yield 10 to 20% amylose and 80 to 90% amylopectin. Amylose typically consists of more than 1000 D-glucopyranoside units connected in a linkages between C1 of one unit and C4 of the next. So this is the C1 and this is the C4. So this is the 1,4 connection. So alpha 1,4 glucosidic linkage. Chains of D-glucose units with alpha glycosidic linkages in amylose tend to adopt a helical arrangement. So this becomes a large chain, this one, this one, this one, this one, this one. So this actually adopts a helical arrangement, and this is the helical arrangement of the glucose units in starch. Amylopectin has a structure similar to that of amylose, that is alpha 1,4 linkage, except that in amylopectin the chains are branched. Branching takes place between C6 of one glucose unit and C1 of another and occurs at intervals of 20 to 25 glucose units. So after 20 or 25 glucose units, you can find a branching in case of amylopectin, and the branching is occurring between the C6 and C1 of these two glucose unit. Physical measurements indicate that amylopectin has a molecular weight of 1 to 6 million. Thus, amylopectin consists of hundreds of interconnecting chains of 20 to 25 glucose units each. Glycogen. Glycogen has a structure very much like that of amylopectin. However, in glycogen, the chains are much more highly branched. Methylation and hydrolysis of glycogen indicate that there is one end group for every 10 to 12 glucose units. Branches may occur as often as every 6 units. Glycogen has a very high molecular weight, almost as high as 100 million. So this is a very, very high molecular weight. 100 million. Okay, million means 10 to the power 6 and billion means 10 to the power 9. Don't forget these two terms, million and billion. The size and structure of glycogen beautifully suit its function as a reserve carbohydrate for animals. Its size makes it too large to diffuse across the cell membranes. Thus, glycogen remains inside the cell, where it is needed as an energy source. It is a ready source of glucose when cellular glucose concentrations are low, and able to store glucose rapidly when cellular concentration of glucose are high. So this is the structure of glycogen, and this is the branching. It occurs after the interval of each 5 to 6 units of glucose. So this is highly branched unit, okay, highly branched molecule. Animals store energy as fats, which is triacylglycerols. So fat is actually triacylglycerol, and as well as glycogen. So animals store energy as fat and also glycogen. Fats because they are more highly reduced and capable of giving much more energy. The metabolism of a typical fatty acid, for example, liberates more than twice as much as energy per carbon as glucose or glycogen. So the energy is actually twice than glucose or glycogen in case of fats. But glucose is readily available and is highly water soluble. As a result, it diffuses rapidly through the aqueous medium of the cell and serves as an ideal source of ready energy. So because of this, glycogen is also needed. So animals have two energy sources. One is fat, which is actually triacylglycerol, and another one is glycogen. Long chain fatty acids, by contrast, are almost insoluble in water, and their concentration inside the cell could never be very high. On the other hand, fatty acids, because of their caloric richness, are an excellent energy repository for long-term energy storage. That's why animals have two types of energy source. Now a question may arise that why can't amylase digest glycogen? Amylase is an enzyme that breaks down starch in the form of amylopectin and amylose. Both amylose and amylopectin are formed by alpha glucose joined together. That means the glycosidic linkage is alpha by 1 to 4 and 1 6 1 4 and 1 6 glycosidic bonds. Glycogen being a highly branched molecule, it is evident that amylase won't be able or won't be good enzyme to digest it due to physical structure constraints. So because of this, because of the physical structure, glycogen is very much highly branched. That's why the amylase can't just digest the glycogen. It is hydrolyzed by glycogen polyphosphorylase. Glycogen phosphorylase. Actually, this glycogen is hydrolyzed by glycogen phosphorylase. I can't utter this. Glycogen phosphorylase rather than amylase. Cellulose. Cellulose contains D-glucopyranoside units linked in 1,4 fashion in very long unbranched chains. Unlike starch and glycogen, however, the linkages in cellulose are beta-glycosidic linkages. So in cellulose, the linkages are beta linkage. The beta-glycosidic linkages of cellulose make cellulose chains essentially linear. They do not tend to coil into helical structures as do glucose polymers when linked in an alpha 1,4 manner. The linear arrangement of beta-linked glucose units in cellulose presents a uniform distribution of hydroxyl groups on the outside of each chain. When two or more cellulose chains make contact, the hydroxyl groups are ideally situated to zip the chains together by forming hydrogen bonds. Zipping many cellulose chains together in this way gives a highly insoluble, rigid and fibrous polymer that is ideal as cell wall material for plants. So this is the two cellulose unit which are coming in contact with each other and these hydroxyl groups are being zipped with the because of the hydrogen bonding property. There is another interesting and important fact about cellulose. The digestive enzymes of humans cannot attack its beta-1,4 linkages. Hence, cellulose cannot serve as a food source for humans, as can starch. Cows and termites, however, can use cellulose as a food source because symbiotic bacteria in their digestive systems that produce beta-glucosidase enzymes. Thus, the special stereochemistry of glucose allows it to form helical structure when it is alpha-linked, which is in case of starch, and this gives a rigid linear structure when it is beta-linked in case of cellulose. Now come to cellulose derivative. A number of derivatives of cellulose are used commercially. Most of these are compounds in which 2 or 3 of the free hydroxyl groups of each glucose unit have been converted to an ester or an ether. This conversion substantially alters the physical properties of the material, making it more soluble in organic solvents and allowing it to be made into fibers and films. Treating cellulose with acetic anhydride produces the triacetate known as arnyl or acetate. It is used widely in the textile industry. Cellulose trinitrate, also called gun cotton or nitrocellulose, is used in explosives. Rayon is made by treating cellulose with carbon disulfide in a basic solution. This reaction converts cellulose to a soluble xanthate. So if you take cellulose and just mix with carbon disulfide in basic medium, this cellulose will form cellulose xanthate. The solution of cellulose xanthate is then passed through a small orifice or slit into an acidic solution. This operation regenerates the OH groups of cellulose, causing it to precipitate as fiber or a seed. So at first you are taking cellulose, then forming a cellulose xanthate, then again you are hydrolyzing it to get back the cellulose unit. This is actually the rayon or cellophane. If you get the fibers, those are called rayon, and if you make sheets from it, then those are called cellophane. So the sheets after softening with glycerol are called cellophane. A process called sizzing chemically modifies the cellulose in paper. As a result, the paper resists wetting. In addition, sizzing leaves the paper in a slightly alkaline state. Acid-free paper lasts much longer than paper that is not acid-free. One sizzing process involves treatment of cellulose with 2 alkyl succinic anhydrides, where the R and R' are short alkyl groups, for example ethyl or propyl groups. These are the ethyl or propyl groups. Glycosylamines, a sugar in which an amino group replaces the anomeric hydroxyl group, is called a glycosylamine. Examples are beta-D-glucopyranosylamine and adenosine. So this is the structure of beta-D-glucopyranosylamine, where this NH2 is actually replacing the anomeric hydroxyl group, and this is the structure of adenosine, where this group is replacing the anomeric hydroxyl group. Nucleosides are glycosylamines in which the amino compound or the amino component is a pyrimidine or a purine base or something like that, and in which the sugar component is either D-ribose or 2-deoxy-D-ribose. That means it may be D-ribose or it may be deoxyribose. Amino sugars. A sugar in which an amino group replaces a non-anomeric OH group is called an amino sugar. So if the amino group replaces the anomeric OH group, that is called glycosylamine, and if it replaces a non-anomeric OH group, then it is called amino sugar. This is the structures of amino sugars. D-glucosamine is an example of an amino sugar. This is the beta D-glucosamine, where this is the anomeric hydroxyl group, and this amino group has replaced the non-anomeric hydroxyl group. In many instances, the amino group is acetylated as in N-acetyl D-glucosamine. This is the N-acetyl D-glucosamine, where this amino group has been acetylated. N-acetyl muramic acid is an important component of bacterial cell walls. This is N-acetyl muramic acid, where this R group is this one. D-glucosamine can be obtained by hydrolysis of chitin, which is a polysaccharide found in the cells of lobsters and crabs, and in the external skeletons of insects and spiders. So this is the polysaccharide chitin, and you can obtain D-glucosamine if you hydrolyze this. If you just break it, you will get the D-glucosamine, and this also will be broken. N-acetyl D-glucosamine is liberated when chitin is hydrolyzed in aqueous acid. Stronger acid brings about hydrolysis of the amide bond to give D-glucosamine hydrochloric acid and acetic acid. So you have taken the chitin, then you are just hydrolyzing it with strong acid, then you will get N-acetyl D-glucosamine, this one, and if you concentrate the acidic strength, then you will get D-glucosamine with the HCl salt. If you apply this part will also be hydrolyzed. Glycolipids and glycoproteins. Carbohydrates join through glycosidic linkages to lipids and to proteins called glycolipids and glycoproteins, respectively. These control the entire activities in the cell. Most proteins are glycoproteins, of which the carbohydrate content can vary from less than 1% to greater than 90%. Tumor cells also have specific carbohydrate markers on their surface as well, a fact that may make it possible to develop vaccines against cancer. The human blood groups offer another example of how carbohydrates in the form of glycolipids and glycoproteins act as biochemical markers. The A, B, and O blood types are determined respectively by the specific A, B, and H determinants on the blood cell surface. The A, B, and H antigens differ only in the monosaccharide units at their non-reducing ends. The type H antigen is the precursor oligosaccharide of the type A and B antigens. So this is the structure of type A determinant, type B determinant, and type H determinant. I don't know much about these things because these are the part of biology, and actually I don't know much more things about biology. So if you are interested, then you can just search about these things. Carbohydrate antibiotics. One of the important discoveries in carbohydrate chemistry was the isolation of the carbohydrate antibiotic called streptomycin in 1944. Streptomycin disrupts bacterial protein synthesis. So streptomycin, the work of streptomycin is to disrupt the bacterial protein synthesis. Now this is the structure of streptomycin. These are the structural units. Unit 1, this one is unit 1, this one 2, this one 3. Other members of this family are antibiotics called kanamycins, neomycins, and gentamicins. Reductones. Reductones are compounds which contain the in alpha diol alpha carbonyl groups. Actually, this will be alpha. This will be alpha. Reductones are compounds which contain the in alpha diol alpha carbonyl group. This is the structure of reductone. Ascorbic acid is not reduced by lithium aluminum hydride. Thus, ascorbic acid does not contain a normal carbonyl group. If it was the normal carbonyl group in case of ascorbic acid, then it should be reduced by lithium aluminum hydride. Actually, all reductones are not reduced by lithium aluminum hydride, and ascorbic acid is also a reductone. This is the structure of reductic acid, which is also a reductone. The reductone means you have a carbonyl group, and in the alpha carbon, the alpha and beta carbons are actually double bonded, and they contains two hydroxyl groups. See this is the ketone group. The alpha carbon contains a hydroxyl group and a double bond with the beta carbon, which also contains the hydroxyl group. In case of reductic acid, this is the carbonyl group. This one is the alpha carbon, which is doubly bonded with the beta carbon, and both of these alpha and beta carbon contains hydroxyl group. This is all about reductone. Now come in detail of ascorbic acid, which is known as vitamin C. This is the reduced form of the ascorbic acid, and this is the oxidized form of the ascorbic acid. Vitamin C was called hexuronic acid. The structure of vitamin C was elucidated by Howard Hirst and their co-workers. The molecular formula was shown to be C6H8O6, and since the compound formed a monosodium and monopotassium salt, it was thought that there was a carboxylic group present. Vitamin C behaves as an unsaturated compound and as a strong reducing agent. It also forms phenylhydrazone and gives a violet color with ferric chloride. All this suggests that a ketoenol system is present in vitamin C or the ascorbic acid. The presence of an aldehyde group was excluded by the fact that vitamin C does not give the Schiff reaction when boiled with hydrochloric acid. Ascorbic acid gives a quantitative yield of furfuraldehyde. This is the furfuraldehyde. If you take ascorbic acid and then boil it with hydrochloric acid, you will get this furfuraldehyde. Now this is the synthesis of ascorbic acid, the mechanism of the synthesis. At first take the L-xylose, then make the 2 position as ketone. You know how to do it. You can make it via ozone. Then add KCnCaCl2, so you will get this structure. Actually, this KCN will attack this aldehyde group, and then after hydrolysis you will get this type of acid, which on tautomerism will give this. And after eliminating water, that means when this OH group is actually attacking this carboxylic group and forming a gamma lactone. This is a gamma lactone because this one is the carbonyl group. So this one is the alpha carbon, this one is the beta carbon, this one is the gamma carbon. So this one is a gamma lactone. So at last you will get the structure of ascorbic acid. There is another process which is in use of the synthesis of ascorbic acid, which starts from the D-glucose, then hydrogenases with the presence of copper and chromium. You will get sorbitol. After that you can use Acidobacter sorbo, I can't see this, what is it, Acidobacter suboxidans. Then use the Acidobacter suboxidans, you will get this structure, which actually after ring closure will give sorbose. Oh. After the ring closure it will give the sorbose. So actually what is happening here, this OH group is attacking this ketone group. So you will get a 5-member ring. See, you can get a 5-member ring, and then add acetone and acid. Then you will get the diacetone sorbose. After that react it with KMnO4, the basic KMnO4. Then something will happen, and what is it? Actually this CH2OH will be oxidized, and then add some acid, so you will get 2-ketogulonic acid. Then if you give chloroform in HCl solution, so at last you will get L-ascorbic acid. This one. Just try to understand, do it yourself.